We'll start. This is for all those who are otherwise engaged today. Welcome to our student. This is the 5th of our seminar series, and we'll go through a couple of the standard things so that everyone's aware. These meetings are recorded and posted to YouTube, so you can review things. Link on edX if you need. We'll be running through the requirements for the next couple of weeks, which really are just the building of your prototype or the specification of your prototype, depending on what approach you're taking. Market research and costing plan we'll talk about a little, and also remember to keep an eye on the discussion boards and join in the discussions to get support and feedback from your peers. As I've mentioned before, we've now finished all the fundamentals of the course. It's now time to be working on individual projects. If you need help, use that email, ask us things. We really are quite happy and keen to help you out with the development. So make the most of it. Contact us, ask questions, etc. We have one outstanding question, but that's only because we're looking for someone with a bit more expert knowledge in image processing. That's that one of detecting a human, Savash, using machine learning.
Yep. We're still waiting for that.
Hopefully Hannes will come back and give us an answer on that today or tomorrow. Okay, so as I said, this fortnight, it's really back down to your working on individual projects. Contact us if you need any assistance or you've got any questions, but we really aren't providing much else on the MOOC site because we want you to be working on things and talking to us. The market research and costing report has been marked, so make sure that you have a result entered in edX. I nearly said Blackboard there, in edX. If you haven't, please let us know and we'll check to see what happened. Savash, you did the vast majority, 100% of the marking on this. Would you like to provide some general feedback?
Sure. Most of the reports were pretty good. For the ones I've given everyone individual feedback. So if you haven't received them by now, make sure to check out your WebEx account, sorry, edX account, to see my feedback. I think the part that most people required a lot more information was with their industry analysis, and then especially with comparison with their competitors. You have to really, even if the industry you're looking at is not exactly the same within the scope of what you're presenting to the market. At the end of the day, the types of sensors they end up using in their project, the types of product, and the way they're presenting the product to the market, it can be fairly similar. So if you can't find a very direct competitor, try to find one within the area that you're presenting your project. And then another suggestion I would have is it's really a good idea to have a look around in Kickstarter and Indiegogo and these crowdfunding website out there to see and search for the key terms within your project and your proposed solution. Because if you're gonna take your scope there, you'll see lots of companies trying to present the same thing, and it could be an interesting kind of another kind of aspect of research you haven't considered, seeing what's out there, and you can take a look at what they're offering to their backers and how much information they're presenting to the customers compared to what you want to present, and in terms of business models and that sort of thing. Besides that, one more suggestion, Ian has mentioned it from the beginning, forgot the name. What was the first assessment we had, Ian, with the Canvanizer? That's the word I was looking for. We highly recommend kind of going back at the Canvanizer you had at the beginning and updating that. The further you kind of look into the project, the more research you do, and then when it comes to the final report, you can use that updated Canvanizer and the market research you've done to finish writing the final report. And I think, Ian, we provided a final report template last time around. Is that still available?
should still be on the edX site.
I think that's all I wanted to mention at this point.
Okay, thanks. Last point on this, we're close to completion of the course. I think we're 10 weeks through of the 14 weeks. So we've created a Facebook page, which you're welcome to join. And the link is there, Curtin IoT6x. If you want to join in, stay in touch with some of the people you've been working with and maybe meet some of the students from past courses. It's not overly active, so it won't fill your newsfeed up or anything like that. But it's a good way just to keep in touch with people.
Ian, just sorry to jump in. We also have the LinkedIn group.
Oh, yes, of course we do. Can you share that
link,
please? I'll have to add that to the
slides, right?
Yep, I forgot about that one. I don't use LinkedIn a lot. I don't use Facebook a lot either, except for work. Okay, so what we're going to be looking at today is heading towards production. So this is a little bit more than just the proof of concept. It generally happens after you've decided that, yes, this is a viable idea. It's going to be both economically viable. There is a market for it. We can actually do what we're saying we're doing. Now we go from our whole bunch of PCBs or whatever sitting on a table to something that is a little bit closer to the device we would be selling to our customers. And there's a lot of different ways of approaching this, and it depends very much on the market quantity you're looking at. So if you're looking at a niche market, you would use a completely different manufacturing method to something where you're looking at a mass market, for a variety of reasons, which we'll look at. So we'll have a look at the software development tools. We've all used the Arduino IDE or something along those lines. That's not the only option we have for development, of course, and we'll have a look at mostly some extremes of this. When you go from doing things on a breadboard, such as the breadboards you find in Tinkercad, with the physical things, you want to start looking at producing custom printed circuit boards. And again, there's a variety of ways of doing this, huge range of cost involved, and we'll have a look at the production there. And the final part is looking at something to hold it all together. And I'll come back to this one, but we go from something like this. Let's see if I can get on the camera. Is that on the camera? Yes, it is. Right, and that's our manufactured printed circuit board. It's not going to go terribly well with a customer, particularly as this is a sonar guide for a blind person. So we need to put it in something to make it usable. And here's one we prepared earlier, which is just a 3D printed case. So we'll look at how we get these things into something that a customer would actually like to use. And again, there's a wide variety depending on the requirements, where it's going to be, how many you're going to produce, etc., and also size. Okay, so starting off with the software development. We've all used this in different parts of the course, I would expect, or we've seen it, or we've used something very similar to it in the simulators. And the Arduino IDE is good in many ways. It's simple. It's very widely supported, so there's lots of libraries to do certain functions. You don't have to write everything from scratch. You can just build on other people's work. It's very quick to change, and that includes a platform. So you can go from an Amiga Nano to a Mega without any really significant changes. So you can actually move across different platforms. It doesn't just do the Arduino ones either, does it, Savash? You can get it modified for many others.
Yep. So with that, they have support for ESP32, which is very popular with IoT type projects. So that helps you work within the Arduino environment, because the Arduino environment is very good to get a very quick prototype done and as a proof of concept, and then later on, as Ian's going to explain, it would be ideal to move into something a bit more professional.
So it has all of these benefits. It's cheap, quick, lots of libraries. However, there are significant disadvantages. It's extremely inefficient. The libraries are not written written for efficiency in mind. So they don't necessarily do things in the most productive way. It's built to be cross-platform, as we've just mentioned, which means it has to allow for all cases. So therefore, the software will do checks it doesn't actually need to do if you're writing your own. It will have separate areas of code that has to call in for particular board layouts. And it means that you're not utilizing the full power of your platform. A couple of other things, it works with the existing prototype board, so you don't actually have to build a board for it. And it's open source, so there's no license fees. And that's something to watch with some of the more professional development packages. Quite often they will charge you for every distribution you use using their platform. It may not sound like much, but it adds up to a lot of money. So just watch the license fees on your development environment. So this is the Arduino, quick, simple, easy, but inefficient. What other alternatives we got? Well, here's a simple one we quite often use. This is, I think, Savash's favorite. So,
yeah, I think that's Code Composer, right?
Yep. And as we can see, it's not quite as simple as Arduino. However, what it allows us to do is look at the architecture of the system we're working with, and we can work much closer with the hardware. And the closer you work with the hardware, the more efficient your software is going to be. It's much more complex, but it's much more efficient. We can embed not only the C code in here, but here we've got some assembly language, which is the lowest level people normally work at with computers and programming. And that interacting directly with the hardware makes it extremely quick and efficient. So you can take out areas of your code which are consuming large amounts of CPU, replace it with much more efficient assembly language, and your system will run faster or on a cheaper platform. Okay, that's another thing to keep in mind. When you design using something like an Arduino, it's inefficient, so you're buying a higher level processor than you actually may need. If you start to use a more professional development package like Code Composer, you can reduce the software requirements so that you can reduce the power of the processor that you're actually using. That may or may not reduce the overall cost of your system, but more importantly, what it'll do is it'll reduce the power consumption of your system. And when we're looking at IoT devices that are battery powered or solar powered or alternatively powered, the power usage is extremely important. So having efficient software running is also crucial to the battery life, etc. These also allow you to do full debugging, so you can look at how the code is running. You can single step through instructions. You can see what's happening inside the CPU registers and look for where you're actually getting bugs or potential bugs and any security issues that are necessary. Anything to add on the?
Yes. So just to add one small tidbit of technical information. When we're talking about efficiency, one of the main things, and as Ian mentioned, is power consumption. And that ties directly into activating low power modes within microcontrollers. And to activate those low power modes, you really need to have that low level control, that assembly level control, because with assembly, that's the closest language we get to a machine language. And that gives us direct control about to manage memory, manage our interrupts, manage the low power modes, and set up your microcontroller in such a way that it's consuming less power. And that's really, it is possible through libraries in something like an Arduino programmer. But here you have, because as Ian mentioned, you have the ability to look inside the register and see what their current value they're holding. That gives you a lot more control, and you end up writing in a lot more efficient code. And the code itself, the size of the code itself is going to be a lot more lightweight, sometimes cut in half because of the because with the Arduino you're putting all of those unused libraries as part of your executable on the Arduino. Whereas if you had the same code but implemented in a code composer, or if you're working with the Texas Instrument chip, IAR is another option. You'll see the size has cut in half. The code is going to be more efficient, and as Ian mentioned, it's going to consume less power if you have used low power modes.
A really good point about the software size. Whenever you're including a library in C, you're including a lot of things that you'll never use, and they may or may not get compiled into the code at runtime. If you're writing the routines yourself in a low-level language like C or assembly, you won't include any of that, and you can actually shrink the memory footprint down quite dramatically. Okay, which again reduces your cost. So that's the software. Now let's have a look at the hardware side of things. A couple of pictures there of different devices. This is on the left is what Savash referred to as a sticky tape prototype. It's a whole bunch of existing off-the-shelf prototyping boards. So sitting underneath there, I think is a Nano, from memory, an Arduino Nano. Here's our inertial measurement unit, which is just a separate board. Here's our wireless connection. The silver bit under here is the battery, and then some switches and connectors to actually get to the thing. It works. However, because it's sort of sticky taped together, and we've got all of these wires hanging around, it's also very, very unreliable. So we found that these were breaking fairly consistently, which was not good because they were out in the hospital system, and of course they couldn't fix them. But it did prove that our concept, our software, did what we intended, and we needed to move it to the next stage. So I actually showed you this one a bit earlier. That was one of our earlier prototypes, still has sticky tape on it, just to hold the battery case, but it's a manufactured PCB. And the other one I've got there is where are we? There we are. Text-to-speech hardware synthesizer. So it turns strings of text into spoken word. The reason we use these is for, again, efficiency in hardware rather than software. And I'll speak more on that shortly, that particular one. So to get us from this sticky tape model of a whole bunch of boards taped together to something like this, what do we need to do? Well, it's actually a little bit simpler than it used to be, a lot simpler than it used to be, and there's a lot of packages out there that will help us to do this. Many of them also allow us to interact with the device and run simulators. So the one I've got here is Fritzing. Again, we mention it in the earlier courses, but from memory, I don't think we used it. We ended up using Tinkercad purely. But Fritzing is a very interesting package to use. It allows you to lay out your prototype board, wire it up on a breadboard as you like. Importantly, from a manufacturing perspective, from this, you can get your schematic diagram. This is what the engineers actually understand. I much prefer, I'm sure Savash does too, to see this schematic diagram than this visual diagram, because this to us is actually hard to follow. This is very simple to follow because it's logically laid out. These packages also offer us the, as I said, the ability to write your software and simulate it on the simulation over here. But for this purpose, we can look at producing the printed circuit board from our graphical wired diagram and have the schematic as well. This is the bit that you need to send to the manufacturer. All right. They can do lots of interesting things, like they can auto route the tracks between components. Generally in cheaper packages like Fritzing, which is sort of free, it may or may not come up with an optimal path, whereas the other ones do give you a lot more flexibility in how you connect things together. You may not think having a direct path or laying the components out in order is important, but as you get into more complex designs, it becomes critically important. And we can see this on the next one. I'd suggest having a play with Fritzing when you get a chance. It is a very good package that is free and can produce these PCBs. It will also link off to manufacturers, which we'll see in a second. So here we have down here the fabricate button. Okay, moving to the sort of mid-range step, there's Eagle. Now this is very popular with our engineering students because it does have the power that you need as a PCB layout. It has a free license for limited. It's scalable, so we can move up through the licensing systems to build very, very complex multi-layer boards. And it's cross-platform, so it'll run under Linux, Mac, and Windows, so you don't have to change your platform to be able to design PCBs. Limited area for the free version, and usually this is how the products set their pricing. The size of the printed circuit board you can do, the number of layers you have on the PCB, etc. And it becomes a little bit more complex to use. It doesn't have simulation, I believe. It doesn't have simulation, does it, Eagle?
No, it doesn't have simulation.
But it links into Tinkercad, which is from the same vendor. But it allows us to have much more control over how the layout is, and the auto routing is somewhat better, and has a few other features which are quite nice, a little bit better than, well, quite a lot better than printing. So this is sort of a mid-range product to be looking at. If you're going for either high volume or very specific markets such as medical or space or others where the quality control and control over the design is critical, you move to something like this one, Altium. Altium is really, really expensive. They've had some big price drops in recent times, but I think that's temporary. You're looking at around about 25,000 Australian dollars for one license. So it's not exactly cheap. Sorry, 10,000. It's 25,000 for. Yep, sorry, $10,000 Australian. So it's not cheap. However, it does many, many things that you would need to do in a high volume or a critical market. We can see here that this is just a capture from their web page. From the PCB layout, it'll produce, do this the right way around. You produce a schematic for it. From the schematic, it produces a PCB layout. And then from there, it can actually produce a 3D model of what the PCB will look like. And you can design the housing for that PCB within the same package. It gives us as you can see, a very complex one here, but it allows us to do other things like a heat map. So Altium looks up the component, it gets the physical size of the component. It also looks up the power consumption of the component and therefore knows how much heat that component will produce. And if you've got a lot of high power components sitting close together, you will get a very hot spot on the printed circuit board, which will cause problems in the future in the longevity of the product itself and the reliability. So the ability to produce a heat map for most of us is not that important. However, in some areas it is, and you would need a package to be able to predict this. It also has several interesting bits like JTAG emulator in there, so you can actually check deborder scans and other bits and pieces on the board itself, and allows for a full testing environment for the PCB, which again, if you're in that sort of market and that sort of product, you'll need to be able to do. And that comes, as I said, at a cost of dollars and complexity. It is not a simple program to use. Okay, so that's the PCB. Producing the PCB has become much easier, but there's a lot of different ways to do this. I'll show you one after this this presentation. But basically, what they require is a Gerber file. Gerber is they've been around for a long time, and they produced the very first automated sign writing robots and PCB robots. So these are relatively simple devices which would actually cut the tracks on a PCB. So once you produce the Gerber file, you've got to send it off to someone to be manufactured. There is a plethora of people who will do this, and it's really a case of picking the right supplier for the market that you're heading for. If you're looking at early prototypes, the online Chinese manufacturer is adequate, and they're very easy to use, and they are unbelievably cheap. And I'll show you a costing on one of these again after we finish. But to give you an idea, we had it was actually this one here, that little ultrasonic device. No, it wasn't that one, it was another one. We had a PCB that we needed to manufacture for a student project. We put it through PCB GoGo. It cost us, for the 9 or 10 of them that we ordered, it was, I think, under $10. So the boards themselves were less than $1 each, and it cost us $25 US to have it posted out. So the postage was more than the PCB's cost. So it is very, very cheap to produce PCBs. That said, they can quite often have some very, very poor quality assurance. We've had problems with this before. It could be that they've manufactured the board wrongly. They've used lead in the design when you've insisted on not having lead, the ROHS, so that you can use it in many other areas. And they can do really silly things because they will actually populate the PCB for you. So that means put all the components on. And I showed you this one before, our hardware text-to-speech engine. We specified everything that we wanted on here and they built it. We got 25 of them made, I think it was, of which maybe 12 worked with the components. However, the cost was so low it didn't really matter. But they made another boo-boo, and that is, if you look at the crystal, that's a silver tin there, which provides the timing for the device, we asked for a half-height one so we could fit it in the case. They didn't have any, so they just plonked a full-height one on there, which meant it wouldn't fit in the case we designed. So we had to go through them, pull that part off and replace it with a local one. And again, that's expensive, particularly if you're doing a large run. Fine for us with a dozen, but if you did 10,000 of these and you've got to remove 10,000 components, it adds significant cost to your device. So going through some of these cheaper manufacturers, but be aware that it may not work. Can you afford to throw the whole lot out? If you can't afford to throw the whole lot out, go to a higher quality manufacturer. There's lots of online ones in the US. We use a local one, Jamel, in Perth. But again, as an example, this cost us about $300 for the 25 made-up boards. Jamel wanted $3,500 just for the boards, not the components, and not put together. So a massive difference in price. Okay. All right. So I'll actually go through this PCB GoGo after we finish, so you can actually have a look. And it's very simple to set up once you've got the file. Okay, last thing we want to look at is something to put it in. And there's, again, many different ways of approaching this. Probably the best for a very small run is what they term a jiffy box. And this is just a standardized black box with a screw down or lock down lid. They're designed so that you can clip or screw in the printed circuit board below it. And the plastic's quite easy to drill, so you can put your connectors on, but they are ugly. They are really, really ugly. So for something that you're producing in very low numbers or is going out into areas where they won't be seen, these can actually be a valid thing to be using. And each of these housings, they only cost $1 or $2 each, so they aren't expensive. You can also get them in weatherproofed boxes, so they have a O-ring seal around them. And again, if you're doing something in an agricultural market, it doesn't matter what it looks like. You can weatherproof it, put it out in the field, and it's perfectly adequate for what you need. The next step up is the 3D printing. And as I showed you, they can be actually quite pretty. Right, so it's not a bad sort of finish, but they're extremely slow to produce. Very, very cheap. The plastic's worth somewhere between $20 and $40 a kilo, and you can make a lot of plastic housings for a kilo of plastic. However, printing something like this takes, from memory, about 6 hours. All right, so it's very, very slow to produce. However, ideal for getting things out for prototyping, field testing, checking the housing design, making sure things are the right shape, size, and are fit for purpose. There's rapid prototyping. Rapid prototyping is something like 3D printing, but it can be vacuum formed or others. And these methodologies are, again, very good for checking that the shape is right, checking that it's user-friendly, but they are not generally used for production or working samples. I hope I got rid of that. I had a picture of a full motorbike that was done through rapid prototyping, and it looked exactly like a real motorbike, except nothing on it worked. But it was used to gauge customer reactions to that particular design. So rapid prototyping is great for samples, usually non-functional, but it's a good way of getting consumer feedback. There's vacuum casting, which is sort of a in-between step. It's suitable for some things. This odd-looking device over here is a vacuum cast housing. They tend to be relatively flimsy, but completely usable, and they're for sort of a mid-range number of devices because it's relatively cheap to make the dies and very cheap to produce. At the top end, as far as production numbers go, there's the injection molding. And injection molding is where we create a mold, obviously, and we inject the plastic, usually plastic, into the mold and produce the items that way. Now, this means that we've got an extremely low cost per item, but having been in the industry and manufactured these dies before, the dies themselves are very, very expensive. You wouldn't be able to get one of these built for any size device for less than about $40,000. So you've got to have a very large number of items that you're going to be selling to be able to warrant this injection molding setup. But the end devices are almost free. To actually start the production is a long setup process that you need to go through on the equipment. Most people won't even look at doing injection molding unless you've got more than several thousand of the devices you want produced, because it's just not worth starting the machine for. Very good for high volume runs. So there's a range of approaches to take as far as the housing goes. And again, much like the other aspects we've looked at today, it's very much based on the number of devices you want to produce, where they're going, what environment they're going into, and the cost you're willing to expend on them. So a lot of care has to be taken in selecting what case to use. It's what the customer sees, so it's what they think of your device. If you think Apple, they all come in very pretty cases and look very nice, and that means they sell really well. That doesn't mean they're necessarily the best phones, for example, on the market. They're nice to use, but they certainly aren't the most advanced in features or things they can do, but they do look nice. What's next? Okay, so just a reminder, weeks 12 through 14 is not actually part of the course. We need to keep the MOOC running for an extra couple of weeks to finalise the marking, make sure that you've got everything you wanted out of the course and happy with any further developments. So we will be running the seminars every fortnight for the next 4 weeks. We've got another 2 to go. David McMeekin will be giving us a talk on location-based services and how GIS fits into geographical information systems, fits into the IoT world. Following that, Valerie will be giving us a talk on big data and data analysis and data science. In the meantime, we will be marking your final reports. So I don't think we've got too many people here. How many more have we had turn up? Sebash?
None. We just had Gopal.
Just a couple. There you go. Individual care. Okay. Can you see my PCB screen now?
Yep.
So what we'll do is we'll change this to, we'll go and manufacture a PCB, pretending we've got the file already. So we pick the type of material, and we'll go for a normal sort of PCB. Single piece, so they'll cut it all up for us. Pick a size, we'll make it millimeters. Millimeters. We'll make it a 30 by 75. And there we go, 75. We'll get 10 of them. It's a simple board. We've only got 2 layers, and if you're not sure what that means, is if you grab a circuit board, like I said earlier, lots of things like this floating around the place. There's the one we've prepared earlier. You can see that the track's hidden under the mask. There's only one layer of copper, a layer of fiberglass, and then another layer of copper on the other side. So that is just a double-sided board. And what it's asking here, we can have 1 layer, 2 layer, 4 layer, up to 14 layers of tracks, which makes for an extremely complicated PCB. We can have very thin boards at 0.2 millimeters or 1.6. We can set the track spacing that we want. which is important when you're looking at the power usage, hole sizes, colors. Whether we want a silk screen. We've got a silk screen on that one, which shows us where to put the components and numbers of components. That's really, really important for when you are building these things yourself, so that you know which component goes where, and also for repair and fault finding. Thickness of the copper, that's 1 ounce per square foot, I believe. That's, again, very dependent on how much power you're drawing, and also the speed of the clocks. Do we want them to assemble a PCB with the components? No. And there we go. So we'll calculate the cost of this. Noting that we've got $28 PT, and they will produce it in 24 hours. PCB cost, there you go, $5. So we can get, that's not each, that is the whole lot. So we can get 10 of our PCBs made for $5 US, cost us $23 to ship it out, and $28 total. So $2.80 per board, which to me is unbelievably cheap. If we go to something a little more complex, let's do a 12 layer, that's where it starts to get expensive. Now 12 layers is a very, very complex board. What's more realistic? A 4-layer board is usually more realistic. We can't do it there. We've got to actually define which order the layers are in, but that will require the Gerber file. Okay, so once we've produced the PCB layout, we can then have them produced. For the PCB assembly, we would actually have to have the bill of materials that go with it before we could actually get a costing on it. Okay, any questions from our students?
Go Paul, any question?
No, I think I'm good. I'm looking at something on the top application, like comparing the trends, all those stuff. So I'm still working on. I could say I achieved how to get the data from a prototype, and for example, I'm storing in a database. Is there any free tool available in like a trending and see the data in the application layer? Because when I tried with Azure, I think I cannot use Azure for free, but I think I'm expert with 1 year. So, yeah.
All right, well, we'll close off. Thank you for coming along, Gopal.
Yeah, thank you.
This will be posted. The recording's about to stop, but we'll post it for everyone else.